For this lesson, we're looking at the dot product, and dot is basically just the way that we're going to be multiplying two vectors together. So product meaning multiply, right? So it's a type of multiplication, and we needed to know Cartesian vectors first in order to move into this 7.2. So operations that we've done with vectors so far have been adding them, subtracting them, and then scalar multiplication. So now the dot product is going to determine mechanical work or work that has been performed on an object, okay? So you might have seen this in physics if you've taken physics before. So what we're gonna be multiplying is the product, multiplying the magnitude of the displacement traveled by an object. So how far the object has traveled. We're gonna multiply that with the magnitude of the force applied in the direction of the motion. And the scalar quantity, where the units are going to be in newtons or in joules. So often for work, we often answer in joules. So let's look at this geometric vector kind of to give an example before we start with an actual example of work done like with numbers and everything, just kind of a general example here. And just to say, sorry, I'm just looking at my notes, a scalar quantity, you're going to get a numerical result, right? Not a vector result, if I didn't already say that. So for two vectors, vector A and vector B, this would be the dot product, multiplying them together, multiplying A and B together is going to give us the magnitude of vector A multiplied by the magnitude of vector B, and then just times cos of theta, because we're looking at the horizontal component. And the horizontal component from the last two lessons has been with cos, right? Remember, if you remember, the vertical component had to do with sine. And the angle has to be the angle between A and B when the vectors are arranged tail to tail. So again, you've got always the last couple lessons, tail to tail, the vector that's in between them, but that angle that's in between them has to be between 0 and 180 degrees, okay? So let's just write down multiplying vector A with vector B is the mechanical work, because mechanical work are those two multiplied by each other, right? And looking at this example, I'm going to use some different colors here to try to explain this further. So let's say the object starts here, just like a circle here. So the object starts here, okay? The motion of the object, it's being displaced, let's say moving to the right, let's say it's being displaced along this line. This is the motion, the red vector. So let's say the object's motion. And then if you can probably guess, what do you think this blue vector would represent then, just like it did in the last lesson, right? It's going to represent the force. This was always the force vector, right? But I should put here, the object starts here. I said it's moving along this. We're going to say that someone is pushing it, just for this example. Someone is pushing the object. So you're pushing it, there's force applied, right? It's moving in this motion. The object's motion is moving along this vector. And then this is the force of the person's pushing for this particular just generic example. So the force of the person's pushing. So kind of like they're pushing it, if you will, like in an upwards motion, like at an angle. So I'm just thinking of something that you would be pushing maybe with your arms, not straight out in front of you, but if you were to lift your arms right over your shoulders, like let's say above your head, and you're pushing in that motion and you're pushing something up, then it would be pushing at this angle. But what we want is we want the horizontal component of that vector, right? So just to change my color here, if we were to bring this, let's say like down, the horizontal, and I'll turn it into a vector here instead of freehand. That would be the horizontal component of the force vector, right? And that's why the horizontal component has this equation, just like I did in the last video, where it was the force of A, the magnitude of vector A, which is the force, times by the cos of theta, because it's the horizontal component of that force vector. Okay, so if you need to write down there, because we want the horizontal component, and that's why we're not using the vertical component, because it's moving in this direction. So for the mechanical work, where can I write this that I might have? Yeah, I can write it up here, I think. So the mechanical work for this particular question would equal, going by up here, just moving it up for a second. The displacement traveled by the object, right? And then multiplying it by the force. So the displacement would be our red B vector, right? The object's motion. So we have the magnitude of vector B, and then we're going to multiply that by our horizontal component. So the magnitude of vector A multiplied by cos of theta. So just to separate those, this part here is the magnitude of displacement traveled. I'm just going to put here magnitude of displacement traveled, short form. And this is what? The force that's applied, right? The magnitude of the force. There we go. So if I have two Cartesian vectors, so for two vectors, vector A, which has point, right, x1, y1, and if I have vector B, which has the horizontal components, right, x2, y2, if I was going to multiply them together, I just multiply my x's together and add that to multiplying my y's together. And when you multiply your x's, I guess it doesn't really matter if it was x2 times x1 and so on, right, if they were flipped or not, but it's kind of good just to go with a standard way that you do it all the time. So let's kind of color code that as well. So just to say that I would multiply my x with my x and get the answer of those two together. You don't need to do this if you think you're good with that, and multiply your y's together, and those two y's will be multiplied together. So properties of dot product. And I should say here that this answer, if you can see, I don't have square brackets around it anymore. This answer would be a scalar, right? This answer would be a scalar. And if you add two scalars together, you're going to end up with a scalar final result as well. A scalar answer, final result. So for non-zero vectors, vector u and vector v, if vector u and vector v are perpendicular, right? So neither one of them is zero, we're saying, but if they are perpendicular, if and only if, when I multiply them together, I get zero. So if I have a vector u, just to show you here, if I have a vector u, multiply that with a vector v, so let's say this one is vector v, doesn't matter, and this one is vector u, right? If I multiply them together, I've got 90 degrees if they're perpendicular then, right? So if they're perpendicular, and if I multiply them together, right, multiplying them, I use the cos of the angle. So the cos of 90, if you try that on your calculator, the cos of 90 is 0. So if they are perpendicular, we'll see an example of that later. If you do the dot product of these two vectors, it would be equal to 0. That will tell you if it's perpendicular. So for any vectors u, v, and w, and let's say I have a scalar k, I can multiply vector u with vector v, And that's the same thing as multiplying v with u, right? Commutative property, it doesn't matter which way it goes. If I had the scalar k times vector u, and then I multiply those together, then multiplied by another vector, that'd be the same thing as multiplying the two vectors together and then multiplying by the scalar, or multiplying the scalar with the other vector v first instead of u first, getting an answer and multiplying it with u, the associative property. And we'll do kind of an example of that later as well, where you can prove that that's true. If I have vector u and I'm multiplying it with two vectors that are added, so I still follow BEDMAS and add these first, that would be the same thing as distributive property, doing vector u times vector v plus vector u times vector w. Or doing vector v and w added together first and then multiplying it by vector u. Then that would be the same thing as, let's say, distributive property kind of backwards here. So I've got v times u, and then adding that to u times w, vector w times vector u. So distributive property. If I have a vector multiplied by itself, then the magnitude of that vector would be squared, right? The length of that vector, if you double it, it'd be two of them, the same thing as squared. And if I have a vector multiplied with a zero vector, so vector u multiplied by the zero vector is equal to the same thing as if I was to switch it, the zero vector multiplied by the u vector. Either way, you're going to get zero if you're multiplying it with a vector that is zero. Okay, let's look at this example compared to that numeric example that I had done. Determine the work performed by a 200 Newton force. So there's our force applied. The force is applied at an angle of 40 degrees, and it's going up a 30-meter ramp. So I have a ramp and I have a force, I have an object that's being pushed up the ramp at an angle of 40 degrees with this much force. So I need to draw a ramp, right? Just to kind of get a visual here. So let's say we do that in any color, straight line. Let's see how this goes. It doesn't say how the angle of the ramp or anything, and I'll show after we do the full diagram why that doesn't matter. So there's our ramp. If we want to just write in, that's our ramp. Okay. Then we have our, let's draw in our, well, we have to do our force and our angle kind of at the same time. Let's do our angle then first. So from the ramp, it's applied at an angle of 40 degrees. So we have this vector at an angle of 40 degrees. So let's say something like this. And that's at a force of 200 newtons, right? There's our angle, doesn't matter which direction, let's say, as 40 degrees within that angle. So 40 degrees, there's my force. Now I have the 30 meters, right? So it's traveled at a distance of 30 meters. So that 30 meters would be the object's motion. So let's just say that that is this vector, the vector of motion it's traveling here for 30 meters along the ramp. So it starts at the beginning, someone's pushing it for 30 meters to the end. The force that they're using is at this angle though, right? And they're pushing it up a ramp. So they're pushing it up a ramp for 30 meters. So what I want, again, I kind of wrote that 30 meters, not in the greatest spot. I'm just gonna move it. Sorry, hopefully you didn't write it down yet. 30 meters is the orange. But what I wanted to say here was I just wanted to bring down. So what I want is I want the horizontal component, right, of the force, just like in that general example. But this is basically, even though I'm on the ramp, this is kind of the direction that the object is going in. This is my displacement line. So I need to do like a 90-degree angle with my force and my displacement line. And from here to the horizontal component of my force, again, that 30 is not in the best spot, that is my horizontal component. Okay, so to figure out the work, it's going to be equal to, again, my displacement first, if you want to just go back and look at the formula on the first page, multiplied by the horizontal component of the force. We always want the horizontal component of the force that was applied. Force applied. So what is that? What's my displacement? My displacement is 30 meters, right? What's the horizontal component of the force applied? So remember that we write down our force, which is 200, and multiply it by the cos of our angle. So the cos of 40, and that is in newtons, just to have both units down, because that's going to change. That's going to turn into something else, right? So 30 times 200, if you wanted, would be 6,000, right? 3 times 2 is 6. 100, but plus the other 0 would be 6,000 cos of 40 degrees, or however you want to do it. Make sure that you're getting an answer of 4,596.3. And again, it's nice to have both units there, because then your answer is in Newton meters. And like we said, work performed, usually we end up writing that in joules. So that's equivalent to 4,596.3 J for joules. And just to mention here, when you're doing your work questions, you're always going to have a positive result. Your work is always positive. Okay, so there's that example. Let's try, I think I can fit this all in here without moving anything. Just doing the dot product of two Cartesian vectors, right? So here's a Cartesian vector. We have horizontal and vertical components. If I was going to dot them, multiply them together, I'm taking my u vector of 3 and 4, and I'm dotting it, multiplying it with the vector 7, -8. And what I do is, remember, I multiply my x's together, so 3 times 7, and then you add to that, multiplying your y's together, so -4 times -8. So that's going to be 21 plus 32, and that's going to be equal to 53. Okay, let's just go ahead and try over here. So for this one, if you remember vectors I and j that we said were unit vectors in the last video, I believe. So we have vector A, which is 3 of the unit vector I and 5 of the unit vector j, so horizontal unit vector and vertical unit vectors. So then A, A is just, if it's 3 of one unit vectors, then that's just 3, right? I'm moving 3 to the right. And if that's 5 of the vertical j vectors, and if I'm moving 5 up, that would be the same thing as just saying that A is 3 and 5. And B, same thing. If I have a vector I, which is a unit vector, then it's really one unit vector, right? To the right, I'm trying to say. And subtract to that 7 of unit j's. So if you're moving up, let's say 7, or in this case negative, I'm moving down 7 unit vectors. That'd be the same thing as just moving down 7, right? So now doing the dot product of those two together, A times B is equal to, again, multiply your x's together, 3 times 1, and then add 5 times -7. So we have 3 plus bracket, I would put the bracket when you have a negative, -35, and that would end up being -32. So also to mention here, if you want to write down, dot products can be both positive or negative. Dot products can be both positive or negative. Here's a positive example, here's a negative example. Okay, let's look at it geometrically. Determine the dot product of each pair of vectors. So I have vector Q, has a magnitude of 24. I have vector P, which has a magnitude of 75, and I have an angle of 135, right? So again, this isn't part of the question, but just to give you kind of a further understanding before we just go ahead and do the dot product of them. This is my displacement vector here, right? just to change my color. This is my displacement. It's moving along there, and this is my force vector, right? So if we look, the force though is going in the opposite direction of the displacement. So if I were to get the horizontal component, right, of my force vector, because that's what I'm always looking for. So if I bring this down, really, I have a vector then that's going in the opposite direction. The horizontal component, sorry, that doesn't look exactly flat, but the horizontal component is going in an opposite direction. So if it's going in an opposite direction, then we should see our answer being negative. Okay, just to get some more understanding of that before we start. So then multiplying, let's say, vector P with vector Q, that's equal to, remember, the magnitude of vector P, remember from before, multiplied by the magnitude of vector Q times by the cos of the angle that we have. So the magnitude of vector P is 75 multiplied by 24 times the cos of our angle is 135. So try that on your calculator. 75 times 24 times the cos of 135. And we also said you could get the cos of 135 times it by 24. When you multiply, it doesn't really matter the order. Just make sure you get negative 1,272.8. So like we said, it would be negative because the force is going in the, you're not putting a positive force. This force is not allowing the object to go in the displacement motion that you want. It's going in the negative direction, right? And also just to know, if you want to write down here, if your angle is between 90 and 180, like this angle is, so if your angle is more than 90 and up to 180, then the dot product will be negative every time. So just to kind of memorize that, if your angle is between 90 and 180, the dot product will be negative all the time. And so just going back up here, I know it's a race, but if you just go back up to this answer here for 2A, right, this answer here with the U and V, we had an answer of positive 53. So if the answer was positive, it means that the two vectors are less than 90 degrees from each other. The two vectors would have an angle between them of less than 90. Okay, let's try this one. You might already remember what we were talking about before about the perpendicular vectors, what you might predict our answer would be. So again, this is our force, this is our displacement vector. This is our force vector. So if you think about the displacement, the object is moving downwards, right? It's moving in this direction, the displacement, but the force is going upwards. So it's not being displaced any further left or right. It's not being displaced horizontally at all. I'm not really doing anything with the force. So when I multiply vector A times vector B, I have the magnitude of vector A multiplied by the magnitude of vector B, remember, times the cos of my angle. So the magnitude of A is 60 multiplied by 50 multiplied by the cos of 90 that's in there. But we already know that the cos of 90 is 0. So I would have 300 times 0, which is just 0, which is what we said. So it proves that they're perpendicular. So again, if you have two vectors and you multiply them and they're perpendicular, you will get the dot product will be 0. So that will be all in every case, right? So just a couple further examples. So here we have multiple. Let vector P have the components -2, 3, vector Q 4, -1, and vector R have the horizontal component of 5, right 5, and up 6, right? Vertically 6. Evaluate each of the following if you can. So we're going to take vector P and minus vector Q and then multiply that with vector R. So let's just write out what we have going on here. So vector P is -2, 3. We're going to minus that with 4, -1. And then we should say that we have to do that first, right? Brackets first, BEDMAS. So put brackets around it and then multiply by vector R, which is 5, 6. So to subtract Cartesian vectors, you subtract your x's together, right? So then I would have -2 subtract 4 would be -6, comma, 3 subtract -1. So be careful, 3 plus 1, if you need to write that down, it'd be 4. And then now we're multiplying, sorry, my square brackets are not looking too good, square. And then when I multiply Cartesian vectors together, if you remember, I multiply my x's together, so -6 times 5, and then I add to that multiplying my y's together. So that'd be -30 plus 6, 12, 18, 24. So my answer is -6. And that would be a scalar, right? So now let's have again vector P. Let's write out what we have going on here. I have, maybe I should just change the color here just to separate them rather than drawing a line. So vector P is -2 and 3. We're multiplying with that with R, 5 and 6. And then we're adding, and in no particular order here, then we're adding, sorry, Q is 4, -1. But I still have to follow BEDMAS. So it doesn't have brackets to tell us what to do, but obviously you need to multiply before you add. So still you follow BEDMAS rules, right? So to multiply the Cartesian vectors together, we have our -2 times 5 added to our 3 times 6. And then we're gonna add, just carry down the 4, -1 vector. So then we have -10 plus 18 plus our vector, 4, -1. So then I end up with -10 plus 18 is, sorry, 8. And I'm going to add that to vector, which vector was this? Q, 4, -1. So we are able to multiply a scalar with a vector together. We're able to add two Cartesian vectors together. We're able to multiply two vectors together, but we're not able to add a scalar with a vector. Okay, so we cannot add a scalar with a vector. So it's not possible to continue. How it says, if possible, what was possible to get to there, but it's not possible to continue. That would be your final answer. Okay, let's look at C here. We have 3 multiplied by our Q vector, 4, -1. And that's being multiplied by itself again, the Q vector of 4, -1. So multiply here and multiply here. So this is what I was talking about, the associative property that we're doing an example later. It doesn't matter what order. I could multiply these vectors together, right? And then I could multiply the 3 in afterwards, or if I multiply the 3 in first and then multiply it by the next vector, you're going to get the same answer. So multiplying this, I would get 12 and -3, and I multiply that, dot that with 4, -1. So then you multiply your x's together, right? 12 times 4 plus your y's, -3 times -1. Well, round brackets. So 48, 12, 24, 36, 48, -3, -1, +3. I end up with 51. And I'm going to leave that up to you guys, right, to show that. So if you want, just take the 3 and multiply your 4, -1, your 2 Q vectors together, and 4, -1, and carry the 3. So again, you'd have 4 times 4 plus -1. Sorry, that's times. This is why I'm not doing it, because I don't want to take up more of your time. Times -1 and go farther, you'd get 16 plus 1 is 17 times 3 is 51. You'd get the same answer, just proving the associative property there. Okay, and our last example, number 5. For vectors S and T, are they perpendicular? And explain how you know. So we've got vector S is horizontal component of 7, vertical component of -3, and the vector T is 3, 7. So if you remember from before, we know they're perpendicular because if we do the dot product, we would get a 0 result, right? So let's just go ahead. That would be the best way to prove mathematically. So vector S dot with vector T is going to be 7, -3, dotted with 3 and 7. Multiply my x's is 7 times 3, close the bracket, add to that, multiplying my y's, be careful with any signs, -3 times 7. So that'd be 21 plus, and again, when you have a negative, I would keep it in brackets. But 21 plus -21 gives me my 0. So that's how easy it is. Therefore, the vectors are perpendicular. Therefore, the vectors are Therefore, the vectors are perpendicular. I'm going to put because B/C for short. The vectors are perpendicular because the dot product is 0. Okay. Based on the observations from right up above here in A, let's figure out a vector. Let's find a vector that's perpendicular to this vector u. So we have a vector u that's got the components 9 and 2. So let's look above. I'm just going to say here, let's look above for a pattern that we can use every time, right? That holds true. So if I had vector S was 7 and -3, and I had vector T and it was 3 and 7, do you notice anything about these vectors that might help us to get a 0 vector with any other question that we have? Looks like the 7 and the 3 are switched with each other, and that this is all positive and this has one negative value. So that's true. We just swap the numbers and make sure that one of them is negative. So here we started out, let's say, with S to start with. Because it was negative, I swapped them. Because one was negative, I made them both positive. In this example here with U, just to write down with U, I'm starting out positive. They're both positive, 9 and 2. So let's just call it anything you want, vector R, vector B, vector V, it doesn't matter. Swapping it with 2 and 9 and just making sure one of them is negative. So -9, or to write down, you could have had vector V being 2 and 9, where the 2 is negative. And then just say here that vector V is a vector that is perpendicular to vector U. Does not look good. Oh. Vector U. Vector V is a vector that is perpendicular because we just called it V, right? So that's why we're just labeling it. We're calling it V and we're making it perpendicular to U. So again, just swap them. If they're both positive, make one negative. It doesn't matter which one, but if it starts out negative, when you swap them, make sure that both end up positive. And you can go ahead, I would say, as a further step here before you finish and start the work, the homework, go ahead and multiply those two vectors together that you just did, do the dot product of them, and just confirm that you get a 0, because that's also just helping reinforce what you just learned in this lesson.